per unit analysis. So anyone who's taken any kind of electronics course knows that this is a very simple circuit to solve. You have a voltage on one side, a resistance on the other side, a current through the resistance, and you solve using the power and voltage equations. Now the problem with power systems is that into the middle of this circuit we have to insert a transformer. And this throws those equations out the window, because now we have a primary coil with NP number of turns, a secondary coil with NS number of turns, two separate voltages across those transformer windings, and a current through the first half of the transformer, as well as a current through the second half of the transformer, which, depending on the polarity of the transformer, could go either way. Now, one nice thing, especially about ideal transformers, is that power is conserved throughout the circuit. That basically means that the power on the left-hand side of the circuit is equivalent to the power on the right-hand side of the circuit. Now, this leads to a very nice relation, A sub t, which is N1 over N2, or the number of turns in the primary coil over the number of turns in the secondary coil. Using this relation, we're able to transfer resistance, current, voltage from either side of the transformer to the other side of the transformer. Now, that sounds simple. However, with power systems, we don't deal with one transformer. We deal with multiple transformers. And this means that even a couple transformers leads to a ridiculous amount of equations. Say, for example, you just want to take the resistances and transfer them all to the left side of this circuit. You end up creating a string, a chain of equations, which it is very easy to get lost in. That's where per unit comes in. What is per unit? Basically, per unit is just the original value over the base value. Here's an example. To find the per unit resistance for the external load here, we would take the original resistance and we would place that over our base for that portion of the circuit. Now, the reason we can use this portion of the circuit to find our base is because these two transformers share a node. So this voltage is equivalent to this voltage, which means we can just use the power equation, V squared over R, solve for R, and that's our base, and use that to get per unit. Now, the nice thing about per unit values is that you can transfer them from either side of the transformer to the other side as if there is no transformer there. So by putting R in per unit, you've basically just removed the transformer for that resistance. Now, this is highly useful for simplifying circuits for power systems. Here's an example. A single-phase two-winding transformer is rated at 20 kilovolt amperes, 480 to 120 volts at 60 Hz. The equivalent leakage impedance of the transformer referred to the 120 volt wind, denoted winding 2, is Z equivalent 2 equals 0.0525 at 78.13 degrees ohms. Using the transformer ratings as base values, determine the per unit leakage impedance referred to winding 2 and referred to winding 1. So the first thing we're going to do is label Z equivalent 2. Then we're going to make sure that we know, since power is conserved, 20 kilovolt amperes is going to be conserved over the entire circuit, thus making it S base. Next, we're going to label the transformer coils and the voltages on those coils, because those are going to be our base values. Now let's organize the base values so we can get to them easily. S base is going to be 20,000 volt amperes because it's conserved over the entire circuit. V base 1 is going to be 480 volts because it is on the number 1 coil, the primary coil on the left. V base 2 is going to be the voltage on the secondary coil, the one on the right, or 120 volts. Now, to find Z equivalent per unit, first we need Z base. But we don't just need Z base, we need Z base 2, because the Z equivalent we're given is already referred to the second coil, or it's already on the right side of the circuit. So we need Z base 2. We get that using the power equation. We need S base, which is going to be the same, but we also need V base, and we use V base 2 because it's on the right side of the equation. So we use V base 2 squared over S base, because that's conserved, and that gives us Z base 2. We can use that now to find Z leakage per unit. To get Z leakage per unit, we take the Z leakage value, and we put that over Z base 2. And that is Z equivalent 2 per unit. Now, since Z equivalent 2 per unit is in per unit, we can basically remove the transformer from this circuit and just use Z equivalent per unit as a new value and work all the equations from here on in per unit and completely ignore the transformer. Now this is really useful even with difficult cases like this. And this is difficult because the two transformers are no longer connected to the same node. They're connected through an impedance, X line, 2 ohms. But you would do this the same way that you would do the past one. You would find the base values for zone 1, zone 2, and zone 3, and then you would convert everything into per unit. And you would get rid of the transformers and just replace them with their per unit leakage impedance, which is that right there and that right there. From there, it's very simple. All you have is a whole bunch of impedances in series or in parallel, depending on what your circuit looks like. And you can solve that using basic electrical knowledge. Now, to put those per unit values back into their original values so you can actually come up with values in voltage, impedance, current, amps, all you have to do is multiply them by their base value in that zone. And you get the value that you are looking for in units. That's per unit.